In May 2026, a high-pressure energy pipeline connecting the North Sea to mainland Europe fails. The massive steel structure simply shattered like fragile glass. First responders arriving at the site encountered something deeply unsettling. They walked into a ghost fire, a pure hydrogen burn that is completely invisible to the naked eye. The only signs of the raging inferno were severe thermal distortions in the air and the fact that their heavy equipment was actively melting. When a standard natural gas pipeline fails, the metal stretches and tears, followed by a highly visible, soot-heavy explosion. But neither of those things happened here. The operators had relied on a standard industry assumption that old, heavily reinforced X70 steel pipes, the legacy workhorses of the natural gas era, were safe to transport 100% pure green hydrogen. Yet investigators combing through the wreckage were baffled. They couldn't find an ignition spark. More importantly, they found zero evidence of standard mechanical wear and tear. The steel hadn't worn out. If the infrastructure designed to carry the clean fuel of the future is spontaneously snapping in the field, miles of repurposed grid are a ticking time bomb. To figure out how a thick steel pipe shatters without warning, we have to move from the disaster site into the laboratory. The culprit is a process called hydrogen-enhanced decohesion, or HEDE. Metals are full of microscopic flaws. When a pipe is pressurized, the area right at the tip of a tiny flaw experiences immense hydrostatic pressure. That tension acts as a powerful thermodynamic magnet, pulling tiny, mobile hydrogen atoms through the solid metal and pulling them at the exact spot where the pipe is most vulnerable. Once those hydrogen atoms accumulate, they slip right between the iron atoms. They act like a chemical solvent, dissolving the electronic glue of the metallic bonds that hold the steel together. The physical design of the pipeline actually made this worse. Thick, rigid pipe walls cannot easily contract or expand. This constraint creates severe internal stress in 3 dimensions, a phenomenon engineers call the tyranny of thickness. That massive stress sucks in even higher concentrations of hydrogen. The pipeline wasn't destroyed by a massive external force. The hydrogen chemically persuaded the iron atoms to let go of one another, drastically lowering the energy required for the metal to crack. Proving this atomic-level sabotage is incredibly difficult because conventional optical microscopes are blind to it. Investigators had to analyze the shattered metal fragments using scanning electron microscopy, bouncing focused beams of electrons off the surface to see down to the nanometer scale. They started by capturing low-energy particles called secondary electrons. Because these electrons barely penetrate the sample, they bounce back to create highly detailed, 3-dimensional topographic maps of the fracture surface. Then they switch to backscattered electrons. These are high-energy particles that drive much deeper into the metal before reflecting back. They reveal the actual atomic density and chemical composition hidden just below the break. This data chart compares what the engineers expected against what they actually found. The top curve shows typical ductile fatigue, where metal absorbs a massive amount of energy by stretching and tearing before it breaks. The lower curve, recorded from the 2026 rupture, is flatlined. The energy absorption dropped to 0. It was a cold, brittle snap. The analysis also revealed a deadly paradox known as the Hall-Petch inversion. Modern nanosteels are designed with ultra-fine grains to be incredibly strong. But all those boundaries between the tiny grains acted as perfect hiding spots for the hydrogen, making the high-tech metal exceptionally vulnerable. The microscopes yielded a definitive diagnosis: intergranular cleavage. The crack perfectly traced the weakened boundaries between the metal crystals, cleanly unzipping the steel without a single trace of plastic stretching. That microscopic fingerprint is the ultimate forensic proof. The pipeline experienced an immediate atomic divorce, triggered directly by the hydrogen environment inside the pipe, entirely bypassing typical mechanical wear and tear. By using specialized 4-quadrant sensors, scientists generated undeniable photometric 3D models that calculated the exact slope and shear angles of the failure. When this data hit the desks of risk assessors, global insurance premiums for legacy energy grids spiked 400%. The industry is now facing a massive retrofit crisis. Current audits suggest that up to 60% of the old natural gas pipelines recently repurposed for the green transition are actively experiencing silent, stress-assisted hydrogen diffusion. To cut the enormous costs of the energy transition, executives actively authorized bypassing a specialized internal polymer lining. That lining was the single crucial barrier designed to protect the bare X70 steel from hydrogen exposure. The legal fallout is dismantling decades of industry standards. Safety and fatigue thresholds established in 2020 are being legally voided in courts right now because the presence of pure hydrogen shrinks the safe operating window of legacy steel to near zero. The $1.2 billion H-Grid lawsuit stands as a harsh reality check. We cannot build the sustainable infrastructure of the future by cutting financial corners on the immutable physics of the past.